Good afternoon. Welcome to this second installment of the .NET Micro Framework. This is entitled Small is Beautiful, so you can read into that whatever you like. For those of you with our previous session, who weren't at our previous session, my name's Dave Baker. I'm an embedded technical specialist based in Microsoft in the UK. I also have a terrible cough. For those who were at the session, I'm still Dave Baker. I'm still an embedded technical specialist, and I still have that cough. I'm going to hand over to Rob, because he's much better at the jokes than me, and he's going to take us through the first section.
Okay, very quick question. How many folk were here on Monday? And how many weren't? Okie dokie. Rumors are spreading. That's splendid. That's nice. We're going to be picking up on the things we covered on Monday anyway, so don't worry about that. I've just thought of a really good micro framework joke, which is there's a company out there making micro framework stuff. They've been so successful they've had to move into smaller premises. Okay, I thought that was quite nice on the micro framework. You don't have to clap or laugh, because I'm going to keep telling them anyway. I've got a piece of paper with 3 emergency jokes on it. I'll save those for a little bit later when the going gets tough. As for now, serious stuff. Small is beautiful. Yeah, okay, I'll go with that, but just about. Large is quite good as well. In terms of what you're going to get, a brief recap of the micro framework. If you've ever watched TV program, you see this previously on Ugly Betty, and you get like a resume. Well, this is previously on Ugly Rob. You're going to get a very quick resume of what we did on Monday, and then we're going to start looking a lot deeper into the code that we wrote and ran on Monday, and look at some of the issues to do with deployment, a big piece on emulation in terms of actually how you can really leverage your skills with C# and Visual Studio to actually make yourself a very, very powerful platform emulation environment that's put your code inside before it even touches the hardware. Then we're going to look at how the display management side of things works, and we're also going to look at a system which at the end pulls things together. So quite demo intensive. All the demo code's going out there. I'm going to put all my stuff out there on .NETmicroframework.com, which is the link you're going to get at the end. We'll do that so you can pull these things down and play with them. So it's all good stuff, and we've got some prizes as well. So there you are. What more could we do? In terms of the .NET Micro Framework, for those that weren't here on Monday, basically it lets you write code for teeny tiny devices using the same tool chain that you're using at the moment. How many folk here write C#? How many folk here use Visual Studio? Right, okay, now you can all rush home, get your CVs out, and add at the bottom embedded developer. Because as of about now, you can now write code for embedded devices. It's that simple. You can take your C# skills, your Studio toolset, and basically you can use the abstractions of the hardware the micro framework gives you, and you can talk to hardware from your software like, oh, well, if you could snap your fingers, you could do it like that, but I can't. I think this hand's broken. Awesome. No, I'm going. Anyway, but you can do it very easily. And you can basically then go further and start building full platform emulations to hit against as well. So as far as we're concerned, what it does is it makes people that are really scared of working in the embedded field, and who can blame them because it's fairly horrible, suddenly very confident and powerful because you've got a really good tool chain to hit against. That's one of the central messages of this talk. In terms of how it works, we have a very small processor which is interpreting bytecode stored in ROM. I'm pretty sure that Bill Gates would approve of the micro framework massively, because it works in a way very similar to how BASIC used to work on the Commodore PET all those years ago, in that we're taking in compiled IL, we're converting it into a bytecode stream, and then the program inside the embedded device is interpreted this in a managed environment. So there's no operating system underneath. Your code can call out and do stuff, and I'll be showing you some code in the demo which looks massively familiar, except for the fact it's running on a machine the size of your thumbnail, which is kind of cute. So it's a very, very simple execution model. It supports all the things you're used to. It's worth making the point strongly and making it now. It's not real time. It's fast. You can use it for a whole range of mobile devices, But you can't get guaranteed microsecond response from this situation because of the way the code runs and the fact you've got things like garbage collection taking place that you can't actually plan for in your code. So we're talking about things like sensor nodes, displays, health monitors, remote controls, data loggers, device controls, robotic elements, anything you want to program to do one small task very well, either on its own or as a connected component. That's what the micro framework does, and you're doing all this in managed code, writing C#. It's jolly good stuff, and that's true because Rob says so. Okay, there is no stronger recommendation. Okay, yeah, this friend of mine has just started going out with a girl who's got X-ray eyes, but I've no idea what she sees in him. Okay, that was emergency joke number 1. I've got 2 and 3. We'll bring those along later. In terms of how the code's written in C# using Studio, if you want to target the real deal, you can do that. Otherwise, you get an emulation. On the slide, you can see at the top, we've actually got the standard emulator showing Hello World in the middle of the screen. At the bottom, we have the Freescale board, which I've got down here, which Dave will be showing you later, showing Hello World in the middle of the screen. Same program running on both. You can walk out of this lecture theatre, but not now, in a few minutes at the end, download the machinery and be writing code for the micro framework like that. Oh, it worked that time. And so it's very, very easy. You deploy according to the device you're using. We've got devices you can deploy via RS-232 or USB or straight down a network connection. So you can have devices hanging off a 10-base-T socket all over the place and just send stuff to these things. You can debug them that way as well. So now we've got code running inside embedded hardware, which you can put breakpoints in. You can do all the good stuff you can do with Studio. On Monday, we had a demo where Dave basically shafted me at the game of cards because he was running his program on a Freescale board that he could single step and salt the deck and see what I was holding. And he was doing that on an embedded device while I was sitting on the other side of the room or side of the desk with a device talking Zigbee over a wireless network. And he was basically actually able to mess around with the code. I didn't even know he was doing it, and it cost me my house. So there you go. Moving on. So all the good stuff, that's how it's built. In terms of the features you get, you don't get all of .NET because A, it wouldn't fit, and B, there's no point. You just get the bits that you need for a mobile device. Serialization, reflection to make that work, RPC, security, full exception handling. You've got delegates and multicast, so you can do all your event management how you like. You've got some good networking support, and you've got managed implementations of all the actual devices, the hardware that you're going to use. If you've ever written embedded, hands up those that have written embedded C and C++. It's not fun, and it's not pretty, and it involves getting data sheets out and finding out which pin does what, and finding out what bit mask goes in the port to make it an output, and then finding out you have to put some no-ops in, otherwise it doesn't happen fast enough and it all goes horribly wrong. It's not nice. In the micro framework, all that's hidden away from you. You get an object which is a pin, and you can basically bind that to a port, and then you can call methods on the port, which will let you control what that port does or read the state of that port. We've got some sample code that does that. I'll show you how it works, and I'll drill through and show you how the emulation of that pin is made to work as well. So you've got a complete virtual environment which you can put your code on, and that has wonderful implications for portability. One of my great claims for fame is that I wrote the code that puts the date stamps on the bottles of Budweiser, and I'm very proud of that. I've got bottles of Budweiser in my office, which has got this on. I had to use embedded C, I had to cross-compile it, I had to build an entire build environment before I could even get a LED to flash. And when I got that LED flashing, I was so happy because now I could actually see something happening in my code. Then version 2 of the product came along, and I had to throw out all my code apart from one small lump because we're using different hardware, different display, different arrangement of the keypad, the whole thing, different chipset. The whole thing was changed, and I was starting from scratch again. Now, if you've got a managed driver situation using common driver specifications, you don't have that. You can change the underlying machinery, and your code will just keep going. And I'll show you how that's achieved as well. So it's all extremely good stuff. You get all the bits you need to make it work. That's the key thing at this level, so it's rather nice. In terms of how it works, I've already kind of mentioned this. We have a mechanism whereby you take the compiled IL, which Visual Studio puts out from the C# program that you've written, And you then basically do some validation, do some compression, map it correctly. I think there's 4 IL instructions they haven't implemented because they're not meaningful on a single-threaded system. You run those through into the device. It says 4 on there, the unsafe ones. You go into the device. When the device wakes up, the processor just loads instructions from the E² PROM and starts to run it. So the idea is that the devices we're targeting here are single purpose. Things like this clicker for the remote control. Things like anything which wakes up and does a job. You put the program in there, and all you want to happen is the power comes on and it works. We've got a queue-based scheduling going on, so that basically the applications, you get your multi-threading, and it's done for you underneath your application. We get garbage collection, so you don't have to worry about grabbing and releasing objects. We also have non-volatile storage at the very bottom there. We don't have a file system as such, but we can do object persistence onto E² PROM in the device using a thing called extended weak references. So the idea is that you'll make an object, you'll mark it as very important, rather important, or I don't mind if it dies kind of thing. And then when you commit, the thing is then saved to the E² and you can pull it back next time, which for the kind of target apps we're talking about is the kind of thing you want. Storing user preferences, all that kind of stuff, data logging, all that kind of thing. It's all you need to use. And so doing all that means we can get the .NET Micro Framework running in a device with about 400K of RAM, which is teeny tiny by today's standards. So very, very small. And with all that in mind, I'm now going to actually jump across and take a look at the program that I showed you on Monday, but in a little bit more detail. So if I do that, followed by that, then how are we doing? That's splendid. Okie dokie. So what I'm going to do now, my colleague here, great chap, he uses his mouse on the wrong side of the keyboard. This is not actually any kind of allusion to anything, how he uses his mouse, but it actually just makes my life really difficult, so you have to bear with me. So what I'm doing now is opening up the project which I created and demonstrated last Monday. And what the starting point of this is, you want to build the ultimate flashlight, or torch, if you're English, a thing which provides portable personal illumination for the 22nd century, okay? So basically you press the button and the light comes on and all around you will marvel, okay? Experience the magic of your own personal illumination assistant. And you can go on like this and write brochures and do all kinds of stuff. But the bottom line, as far as I'm concerned, is we're powering this with .NET Micro Framework. It's actually the example used in the book, which I'll continuously mention because I wrote half of it, and which you can buy at all good newsage bookshops, but not the one that's here, unfortunately. Life's like that. But basically, it's an example to show you just how easy it is to write a piece of code, put it in a device, and use it to turn the light on and off. And so, I mean, what I will show you before I do that, though, is just the process by which you actually make a new project. I'll just very quickly drop into this because it's worth mentioning. The way it works is you've got Visual Studio, any version apart from Express, so Standard, Professional, Team, Foundation, you name it, any of those will work fine. You install the code. It's very much like writing code for the mobile devices, the smartphones, the pocket PCs. You bring the SDK down, you install it on your machine, and lo and behold, you get an extra project type or two. And in this situation, we've basically got the micro framework. And what I'll show you here is the options you get for new projects. You can build a class library, so you can share code amongst applications. You can build a console application, which is just the kind of thing you'd use in a headless device. Quite a few of the micro framework devices don't have displays, don't need them. They just sit in an air duct or something and just do their thing, powered off a network or whatever. No need for a front end, so we don't bother building one of those. Makes the actual program simpler and smaller. There's the window application, which all that really changes is the way it configures the emulator and the actual default project that you get, and that will display a little window. We'll talk about display driving a little bit later, and we'll also talk about the business of device emulation, which is the third kind of project. Because what you can also do with this setup is build your own emulator. The problem I used to have when I was writing code for Budweiser was that the laser was about the size of this desk, And when you fired it, walls used to catch fire and things. It was quite cute like that. And I couldn't really have one of these in my bedroom when I was writing the code. So I had to build a complete emulation of the environment in which my program was running so that I could toggle lasers on and off and not actually have to have the real one there. So a big chunk of any embedded development process is, how am I going to test this thing? How am I going to prove it works? How can I put it into situations that I'm going to need to show it can behave, but I don't want to do that in real life? And the way you do that is by putting an emulation around the actual thing you're making. And one of the things that's really powerful in the microframework is just how easy it is to do that. And the starting point is always the default device emulator project, which you can then configure and make point at the particular device platform that you're actually going to head for. Now, the way it works is that in the case of my flashlight, I've been and talked to my hardware man, and he said, okay, Rob, he said that pin 1 is the lamp and pin 0 is the switch. I thought pin 1 and 2, sorry, pin 1 is the lamp and pin 2 is the switch. And I've gone, okie dokie, I can now get my code to work, build an emulator which behaves that way, and I'll show you that in a second or two, and then off we go. So as far as we're concerned, free download, straight into here, default emulator, so you can start writing code, writing test harnesses, writing all the bits and pieces you want to have to prove it works. You can even bring in some code that you've already written and drop that in, because it's all C#. It all just compiles down to assemblies that all just run, and then away you go. So what I'm going to be showing you just right now is something which I've written. I've just pressed the wrong button. Oh, mother. Okie dokie. Let's just get rid of you and start again. Okie dokie. Here we go. I wrote the code, hit a pretend device, an emulation. But if I want to, if I can find someone daft enough to actually give me 10,000 million pounds to venture capital and make the ultimate personal flashlight, then that would be great. But I've basically got a system which will prove that it works. And I can actually show you this going in that what we've got here is an emulation of my flashlight emulator. And the idea is if I press the button, the light comes on. And if I press the button again, the light goes off. And if I press the button again, the light goes on. Now, this actually doesn't stay interesting for very long. And it's certainly not worth applauding. So I'm very glad that nobody clapped. That would have been so embarrassing for everyone concerned. What you can also do with my flashlight, because it's kind of funky, is we've got, if you look very carefully on the top, you'll see flashlight emulator E²PROM. I've made a version of the emulator which actually persists the data for me. And so the idea here is that we can log the use of our flashlight. The idea I had here is you've got a bunch of security guards who you don't quite trust, which is a bit dangerous, really, if you think about it. But anyway, these guys are supposed to go off around the plant at night doing security guard things and waving their torches around and pointing them at stuff. So wouldn't it be great if you could log the use of the flashlight? So when they come back off shift, you can say, no, you haven't been using your torch, therefore you can't actually have been going out on duty. And so they'll be sitting in their office going do-dum, do-dum, do-dum all night with their feet up watching telly. So the second version has a GPS in it, which is what we'll be showing a little bit further on. And with that, you've actually got a really quite a powerful management tool. Anyone see the screen flash a few seconds ago? It flashed yellow for no good reason. There it goes again. This is the ultimate flashlight. It has a finder feature. If you actually, the thing about torches, you need them when it's dark, but then you can't find them. Now, to solve this problem, which I spotted quite early in life because I am that clever, what you can do is basically the torch will flash for 1/10 of a second every 5 seconds. So if it goes dark, you can find it. And so what we're going to do now is really explore, oh, my serial comms, I'll make you do that first. If I send this thing a D, D means dump. And if I press the send button, it dumps the on and off behavior. So if I flash the light a few more times using the button, right, so now I have some more events in there, so I can now just go there and get my log. And so what's happening here is that I've configured the emulator with a serial port. So in real life, and we'll show you this as well, the device plugged in, I can send RS-232 into this thing, it will respond and talk back to me. And so what I've got to make that work so I can prove it goes, I've built an emulator which has a text box, a button, and a text field, which shows the messages coming back. And so I can actually inject characters into my flashlight just by putting them in there and clicking send. and it then responds with the information. So I can prove that my logging stuff all works without having to make the real hardware. What I want to do now is just do a bit of digging around inside the actual code and show you how it all fits together. Okay, so let's start at the very beginning, which is not a cue for a song, thank goodness. If I drill down here into the code, let's have a look at our main method. The thing I want to show you first is up here, this stuff here. Effectively, at some point, I have to do my mapping of the hardware into the actual real code. And this is the point at which I do it. I've got a pin 1 and a pin 2. One is the lamp and one is the switch. And so I make a couple of pin instances that define those two physical connections. That's the point at which I'm tied to hardware. Once I've done that, I then move further down. I make myself an output pin, which is going to be bound to a physical pin, and that's an object-based abstraction of a physical device. So I can call methods on this thing to make the pin go up and down. And so the two things I have to tell the output port constructor are which pin you're going to use and the fact that initially I want you to be turned off. So when the pin is first created, so when the port's first made, we say you're not set high. So the lamp is initially off, which is what we want. Okay? Then we move down and look at the second port I'm going to make. Now this is a bit more special because this one we're doing interrupt triggered events. The first flashlight I made on Monday used a hold technique where if the button was held down, the lamp was on. When the button came up, the lamp was off. The snag with that is we have a tight loop running, which doesn't waste processor resource particularly because there's nothing else for this device to do. It can just sit there and run flat out all the time if we want. But what it does do is it flattens the battery. What I really want is to get everything set up and then put my processor to sleep if I can. So what I'm going to do is bind interrupts to the events where the pin goes up or the pin goes down. And that's what this bit of code here does. So make myself a port, tell it which pin to use. A glitch filter is a way you can ask the actual pin hardware, the port hardware, to ignore short transients. So if you want to actually do a bit of debounce filtering on your signals, there's an option to actually select that in the hardware, in the constructor of your port. And then basically you've also got a bit more hardware. What this means is that under normal conditions, the pin is pulled low. So when I press the button to turn the light on, what will happen is the button will link the pin to the supply voltage to pull it high. So when the pin goes high, that's when I want to get my signal, so I pull it low initially. Now, from a software point of view, makes no difference. From a hardware point of view, I have to go and see my hardware man and ask him, okay, which way does the pin go? Which way does the port go up and down? Because I need to configure that as well. And then here, I'm saying, okay, if you get an edge, whether it's a rising edge or a falling edge, I want an interrupt. You could say, just give me the interrupt when the switch goes down, or just give me when it goes up. I want to see both of them, because when the thing goes up, the light goes on. When it goes down again, the light goes off. And having got my port, I can then bind a handler to it. It's sitting down there. So the next thing I can do is basically bind a handler there. And if I just, we'll take a look at what happens in that in a second or two, because we'll keep on going through our main method and getting our things set up. What I'm doing, you've already seen, is that we've got this, this rather nice flash finder service where it flashes yellow every 5 seconds or so. Wonderful. How do you make it work? Well, you make a timer. And anyone that's ever made a timer on .NET will find that code remarkably familiar because it's the same stuff. It's the same deal. So we're basically binding a method to the timer events, 5,000 milliseconds to the first flash, and then 5,000 milliseconds after that to get my 5-second flash rate. And so what happens is that every time the thing goes tick, we get a call of this method. And if you want to see what the method looks like, let's just go and have a look at the definition of the method. Here it is. Then I read the port to see whether it's gone up or down. If the, this is going when I'm going tick. If the light's on, no point in flashing it. So I read the input port. If he's holding the button down, I don't want to do a finder flash because there's no point. If he's not holding the button down, turn the light on, wait 1/100th of a second, and then you have an issue. Bless me. What's brown and sticky? A stick. What do you call a boomerang that won't come back? A stick. All right, fair enough. Let's move forward. Even you kept a straight face through that one. He's just thinking, oh my God, my life is so over. Right, moving on. Why? That's right, fine. Okay, back to the plot. If we just happen to have the lamp flash at the time the user presses the button to turn the light on, there's a 10th of a second window in which we have a timing issue. And if they turn the lamp on whilst I'm flashing, I'll turn it off, and the user will have what we call a bad user experience. Because the light won't be on, okay? There'll be dissension in the ranks and much muttering. I have to resolve that. The way to do it is to actually do some proper real time, put a monitor on the thing, and then make sure that when I actually do the business of, if it's not on, I turn it off. And I don't want to be interrupted in that process. So I'm using standard monitoring techniques here so that basically I enter the monitor, I exit it, and in the middle, I read the port, and if the lamp isn't on, so if the switch isn't down, I turn the lamp off. Now, the only reason I'm really showing you that is not to show how clever I am in making torches work, although this is, of course, true. It's really to show you that this is not news. This is the kind of stuff you'd write to solve threading application issues on mainframes, whatever you like, big machines, little machines, pocket PCs, you name it. This is how you do it. It's how the micro framework works as well. So there's nothing new here. There's no magic here. It's all just exactly what you would expect, working in just the same way. If we continue chugging through our main method, next thing I do is set the serial port up, which is simply a matter of configuring the baud rate I want to use and the actual format of the serial data. And then last thing I do, on the micro framework, the serial port isn't interrupt driven. It's actually, you go off and see how many bytes you've got. That makes good sense, because I don't want my program being overwhelmed by huge numbers of interrupts just because the data stream's arriving. So I'm going to have to go and look for my characters, but that's not a problem because I know how to do that, because I know all about threads, because I've been writing C# for years. So I'll just make a thread, and the thread basically will spin, waiting for characters to come down here. If I go and have a look in my method that does this, then it's exactly what you would expect. Spin round, wait a little while for some characters. This is the read method that you call on your serial port. And what I'm doing is I'm waiting for 500 ticks. And if I get some characters in that time, then I'll look at the first character in my buffer. And if it's a D, which is the one I use to queue the output, then I call the method to just squirt out the code. So that effectively, again, the reason I'm showing you this is really because I want you to understand that there's nothing magic happening here. We're just using the standard .NET mechanisms that we're using from C#. We're not actually hitting an operating system. We're hitting the runtime, which is sitting underneath my program. But that just doesn't matter. It's not a problem. It all just works. So having seen that, we've actually now got quite a nice understanding of where it goes. And of course, like all the best programs, the actual code itself does nothing. I put a while true around there. There's absolutely no reason why I should do this. But I'm the kind of person that walks away from his car, then walks back and sees it's locked, and then walks away from it again and walks back, because I'm a bit like that. And so if anything should happen to cause that sleep forever to come back, I'm going to go round again. But generally speaking, I've got all my interrupts set up, I've got all my timers running, I've got everything out there how it should be, so I go to sleep and then wait for things to happen around me, which is what I do at home apparently as well. That's the other joke. No, it isn't. That's a different joke. Okay, moving on. If you want to see what happens when the light goes on, then you basically go down here, and what you find is that effectively we've actually got some more monitoring to do, but effectively I'm making myself a record which I'm going to store, which has got the information in there, and that's actually the bit that turns the lamp on. Now what I want to do in the third demo of this sequence is drill through this code to show you what the emulator does and how that's been bound into the process. But as far as we're concerned for this part of the demo, that's pretty much where I am. I've shown you how it all fits together, and I've shown you how the code works. And what I really hope I've shown you is no surprises, because it's just like the code. Apart from the object model for the actual hardware, there's nothing else magical or special going on here. It can't be that complicated, because if it was, I wouldn't be able to understand it. And that's definitely the truth. So what I'll do now is I'll hand over to Dave, who's going to take us on to the next bit.
I've got a screen. Yes, I have. Right, no jokes in this bit, okay? So take that as you will. So Rob's been through a number of features here in terms of what the microframework is capable of giving us. We've looked at it from the perspective of our tool chain. We've looked at it from the perspective of how we can use Visual Studio to be able to achieve all of this great stuff. So there's debugging, there's emulation, there's all of that wonderful stuff in there. We've also talked about how we can target limited resource devices. Really, when we're getting down to this very, very small level, we need to be able to optimize. And also, we've talked here, very well around how can we use the emulator, not just as a way of debugging our applications, but as a way of designing our applications as well. You can see here that Rob has a torch, which he'll possibly go away one day and speak to a venture capitalist who'll laugh and tell him to go away. But who knows? Maybe he may make his first million, if there may be £1 million each. So what we really need to look at is, what does this mean to the developer? What does the developer actually get out of this platform? Well, we get an API. We've talked about this. It's called the .NET Micro Framework. We've got graphical options. We've got multiple ways of being able to write things up to the screen. And we also have ways of persisting data onto that platform, not as a file system, but such a way that we can actually get through power cycles. We can get through power outages. Think of situations, these devices, they could easily be in ducting somewhere or on a building where it's inaccessible. You get a power outage, the power comes back, you don't want it to have to be reset. I don't want to climb that ladder through that ducting or up that building. So let's start with the framework. It has to be smaller. We wouldn't be able to fit it in 400K if it wasn't smaller. And the .NET framework is megabytes. We're talking 400K. It makes a big difference. Now, the thing is, though, is that you actually, for this type of application, have absolutely everything that you need. So the elements in yellow up here, so I/O, reflection, threading, they are straight ports of the .NET framework. So the implementation there is exactly the same as implemented in the .NET framework. If you look at drawing, if you look at text, if you look at interop, again, these are not direct ports of that, but actually they are optimized to be able to fit onto this platform. So they give you everything that you need to be able to design and write that application and to be able to drop that application out to these small scale devices. So it's small, it's cut down, yes, but you've got absolutely everything that you need. Now, we've talked about graphics. Rob always does things in theory, he always does things with emulators, and he never has graphics. But actually, if you look at this type of application, I'd say graphical applications are probably in the minority for these type of devices. I could be wrong there, but actually, you're looking at highly pervasive devices, devices that are going to be network powered, that are going to sit in inaccessible areas, but are going to be remotely updatable, and it's possible to be able to query those devices, to be able to pull information from them, to be able to update them as you wish. Now, we actually have two ways of being able to drop graphics out onto one of these devices. We've got familiar, simple bitmapping methods. You can use this to draw shapes, you can use this to do simple rendering, things like that. And you want to do this where possibly resources are constraint, performance is a constraint, and also where speed is a constraint. So if you were going to write a micro framework game, then you would probably do it using this. We also have a WPF style type of rendering as well. So what this gives you is a means of being able to support more complex ways of deploying images out to that device. So be that through layout, through canvases, through stacks, all of that familiar stuff. You can use that type of method to be able to address the graphics on these devices as well. There are several differences. So if you notice, I used style in there as part of the description. So one of the things that you'll notice is you still have to invalidate. And the reason you have to do that is actually because these are low power devices, you don't want them constantly invalidating updating their displays when you don't want that happening. Actually, you want to be able to force that, to be able to make it happen when you want it to happen, so that you can ensure that you get the best performance out of that display in terms of its power consumption and in terms of its usability. Now, we also talked about storage. Now, mentioned on a couple of occasions in this session, in the previous session, the .NET Micro Framework has no file system, none whatsoever. However, it is important that we can persist data. As I said previously, power outages, power cycles, things like that, we need to be able to persist that data between system reboots. And the way that we do this is that we actually use extended weak references. And we can store .NET objects, we can store values and things like that, and then we can address them effectively by their IDs. The way we do this is within the garbage collection, what we can do is we can decide, rather than these items being thrown away at any time, we can choose to actually persist them for as long as we need them. So this gives us means of saving setup information, configuration information, IPs, things like that, so that the device will reconnect if it ever gets disconnected for any reason. Now, just to sort of give you some example here, what I thought we'd do is we'd perhaps dive into some code and look at some graphics here. One of the main reasons is because Rob, again, has used emulators and he's used torches and things like that, and I just love doing the stuff around the graphics displays and understanding how that works. So let's first of all show you what we're looking at. So this is a Freescale micro framework board. It actually has a temperature display on it at the moment. What I can do is I can adjust this temperature display and set the desired temperature up or down. And what you can see is that as I cross through the existing temperature, it'll switch my air conditioning off. If I go above it, it'll switch heating on for me. Now, essentially what this is doing is this is just checking a temperature on an input port. It's running it through the system here. And what it's doing is it's doing a render for me on this screen, an instantaneous render of this information. So let's just fire up the application. And let's have a look at what we've got here. So if we go into Create window and we start working our way through this, then what we can see is that we go through sizing our window. This application will actually run in portrait mode as well as landscape mode. And then what you'll see is actually here, we're going to build ourselves a stack. The stack represents the entire screen. What we're then doing is we're going to create two panels. These are the borders. These are the two areas that you saw, left and right. And then depending on our orientation of our screen, we're actually going to split that either left or right or top to bottom and things like that. So actually you can see here how we're setting our panels up depending on the orientation that we have our screen. What we're then going to do is we're going to actually create ourselves two further stacks, one stack per panel, and then what we'll do is we'll actually add those stacks onto the panel. This all looks familiar. This is just standard stuff. If you're familiar with WPF, it's using exactly the same stuff here. And then we're adding both of those panels back into the original stack, the full screen stack. And then what we're doing is we're going to create ourselves some text. So this is the left side of the screen. So this is the area which is showing the current temperature. So you can see we've set a default. We're going to set the horizontal alignment to center along with the vertical alignment. We've here got the label that sits above it. And then what we're actually going to do is we're just going to add both of those into the stack. Now we do the same for the right-hand side. So what we're doing here is creating ourselves the desired temperature, the label that goes with it, and then what we've got here is the status indicator. This is that little icon which said whether we're going to be cooling or whether we're going to be heating. And basically what this is an object in its own right which actually just displays that particular image. So you can see over here that we have the fire and snowflake resource, and that's effectively what it's going to pull in. Now we can add in our labels again. We can add in our status indicator. We can flow a bit of text after it. If you remember, there was some instructions on there on how to use the device. And then basically what we do is we hit the stack with it. Now, Rob went through some of this, but just to show how it works on a real-life device, you saw me hit some buttons. You saw the temperature go up. You saw the temperature come down. Well, here it is. We've wired it in. Here's the events that's actually triggered in doing that. So we've got button up and button up button and down button events. And effectively, what we're doing is incrementing and decrementing the temperature around that. And then we're calling a method called update UI. And if we run back to the update UI, what we can see here is we will update what we're looking at on the screen. We can even change between centigrade and Fahrenheit on this. And then here we go. What we're doing here is we're actually setting the sensor image based upon whether we're above or below that temperature. Now, if I shoot down to the bottom and I find our status, there we go. So there's the status that was being called as part of that. And what do we find right at the bottom of it? Invalidate. So what we're actually doing is every time we do a temperature sense on this, we run through that whole process to decide whether anything is changed, and we only actually invalidate the screen if something has changed. We don't invalidate it, in this case, every second, which is when the temperature is coming in. So moving on to the emulator. We've talked to it. Rob gave a great demo of what the emulator is capable of doing for us. But we need to look at the emulator in terms of not only a tool for being able to develop and design your applications, but also something for being able to develop and design the ultimate hardware for your solution. So you're no longer constrained by having to get your hardware, specify what that's going to be, even before you've written your solution and designed your solution, and then doing your development against that board, possibly using bespoke tools, possibly using bespoke languages to do that. What the emulator allows you to do is actually to walk away. So you could do it today if you've got Visual Studio, you go into download the .NET Micro Framework, you install it, you can build yourself an emulator application today. You can do all of your work on that. You can define what's required as part of that hardware, and then you can go away and specify that hardware and build the bill of materials to be able to build your device. So it makes us very agile in designing and developing solutions. We can emulate devices as well as the processor. So actually what we can do is we can hook devices, virtual emulated devices, onto the solution. First of all, to understand how the inputs and outputs are going to work, but also what we can actually do is we can also emulate behavior of those devices and behavior of the components. So actually we can actually start talking about how we can automatically test our solutions using the emulator that will, as part of the development process. So this diagram gives you a pretty good overview of what the ethos of the .NET Micro Framework is. This is how the emulator works, but actually this tells you exactly how the .NET Micro Framework works as well. If you look over on the right-hand side, we've got our Micro Framework application. Now, for those of you who were in the last session, we built a solution for an emulator, and then we built a solution for hardware. And actually you could see that it was exactly the same code, but what we were doing is we were just sending it to a different target. We would choose our hardware or the emulator. It's the same code, come what may. Now, in the case of the emulator, what we have is an x86 version of the Tiny CLR, the Micro Framework. So we're hosting that on top of the Windows platform. And and then an x86 implementation of the hardware instruction there, platform instruction there. And then what that does is that hooks down into the emulator. Now you can see that there's a load of devices in there. They're available straight out of the box. That's GPIOs, RS-232. All of those external ports are available out of the box, and you can emulate them directly. But you can also add your own components in there as well, and you can customize that yourself. Now you can see there's also a configuration engine. Now Rob showed you an emulator of the flashlight. Now that had a user interface on it. He'd hooked the buttons on the screen to the physical buttons on the device. He'd even shown how the flashlight would come on and go off. And actually what you can do is you can create that using your own component, using your own application to specify the UI. You can also configure through XML what the capability of your device is going to be. So things like available memory, screen resolution, things like that. And that's all dynamically configurable through XML. And actually, again, is a very powerful tool, because what you can do is you can specify the platform, which is your desired platform, and then what you can do is you can throttle back the capabilities within the emulator down to the minimum specification that you may need to be able to build that hardware. So you can physically test different hardware capabilities within the emulator. The one thing that we have to recognize with this is that the emulator, one thing that it can't do is it can't give you accurate cycle timing, because what we're doing is we're running it on a completely separate processor. There's a flip side to that in emulation, you can actually programmatically stop time if you so wish, test things, move on, but it doesn't give you the ability to test that performance. So then, this is why I like this picture. This is the full implementation. So this is if it was going down to the hardware. This is it in the emulator. The bit on the right-hand side just doesn't change. So actually, we're dropping our original code into the emulator unchanged, no modifications. And that's the same as the code that we will actually deploy. In this case, we then have the tiny CLR for the hardware platform that we're deploying on and the custom hardware abstraction layer. Or as we discussed in the previous session, it could be a platform abstraction layer where this is hosted on another operating system. So as we talked about, emulation is at the platform abstraction layer level. The code above that layer is exactly the same. We talked about the fact that performance is not cycle accurate. Another thing is, obviously, you can't test PAL or HAL development within the emulator because it's an integral part of the emulation. So there's some areas where you would need to go outside of the emulation capabilities. But outside of that, you can run your application within the emulator in exactly the same way as you would on real hardware. What you can do is you can debug, you can trace, you can set watches. You're running it in the emulator as if it was on real hardware. So with this, I think Rob's going to run into another demo, and there's some information here which is probably going to help him in explaining that. So I'll hand on back to Rob.
Thank you. Question beforehand. David's mentioned it, I've mentioned it. What's the smallest memory footprint you can run this thing in? Who said 400K first? Who said 400K? Anyone said 400K? Who's going to get that? The first person that said that, it was the first person that said it wins the book. So who said it first? Him. Oh, okay. Can we give it to a man in a speaker shirt? This is the book. This is the book which defines the thing. I wrote the good half of it, and there you go. For knowing it's 400K, you may have the book. As I say, you can't get it in the shops. It's that good. So what having totally got that wrong, I do apologize, but you can all buy your own and whatever. If you want that signing, then sign it yourself, so don't sign books. What this is showing you, when we get to it, if I can just put a little red dot, is the actual the code that configures what the emulator looks like. So this defines the platform under which my code is going to run. And this is what makes my microframework torch work, in that I've got a pin 2, which is going to be my push button, and a pin 1, which is my lamp. And I give them names, and I tell the emulator, okay, this thing is allowed to be an input port, and this thing is allowed to be an output port. What that means in software terms is if I try and read from the output, it won't let me. So if I try and do things that are meaningless, I can make things bidirectional if I want to do that. But if I don't, then it's a good idea to have the system tell me you're doing something stupid. Now, in real hardware terms, you wouldn't get that. If you're writing C++ on an embedded device, you try and write to the input port, then bad things happen. That's all we can say. In this situation, what happens is the emulator says, you told me you weren't going to do that, throws an exception, and your program stops, which is really rather nice. So it's basically an XML file which you can edit, and you get a default one with the emulator when you install it, and then you start playing with it. What I've got here is the thing you've already seen, and so effectively, we've got a situation where we can build a complete platform around our application, or if we want to, multiple platforms. If you want to actually test it on several different configurations, that's all fine and dandy, and that is how you do it. You can make your own component library to go with it, and I'll touch on that in a second as well, because the next slide moves us on to the demo and gets in terms of how we're going to build an emulator. So I have to press that button and that button. I'm going to go back onto the show and move the mouse for a normal person to use. And so now we can see what we're doing. What I've got here is I'm going to take you through and show you the emulator which I built. And then finally, I'll show you the big fangled posh emulator which I use to underpin my micro flathead. So we just dive in here. This is not a program I will ever run, but it is a program that I will build and install. The way it works is that once you've actually built an emulator, it then becomes part of the repertoire of emulation features on that machine. So I'm building a thing called Micro Flashlight Emulator, and what this will do is provide the behaviors that actually sit behind the software that I'm going to be running in the real device. And if we take a very quick look, you'll see the familiar site of the actual form. And what the form is doing is implementing the checkbox, the panel, and the text box, the other text field, and the send button. So this is my front end. And I just sat down and made a little class to implement this, and then away we go. So there's nothing particularly special or magical about this. The fun starts happening. Well, the thing I'll just show you very quickly before we go any further, though, is a very familiar page, which you should have already sort of seen in one form. This is actually the file. That's the file that contains the information that configures it, the one we saw in the slide. So this is basically the thing that does my mapping. I've created some physical devices. I've given them names. I've got a push button, a lamp, and a serial port, and I'm mapping them onto devices, pin 2, pin 1, and universal serial input, USART number 1 for my COM port. So as far as the micro framework application is concerned, it's running on a device that has an input pin, an output pin, and a serial port, and nothing else. So that's where it's coming from, that's what it's using, and this is the code that actually does it. And what I want to show you here is, we go back to the top, there's a process by which you actually build the emulator. There's a sequence of method calls that run in the emulator program itself to get it to sort of pull itself together, boot itself up, and get itself going. And what I've got here is the code that does that. When the emulator fires up, it reads the XML, it builds the devices it's going to emulate, and then it gives you control by calling the initialized component. And what I do is I go off and I find those components, I get them from the emulator, and I make my own references to them. So here you can see I go off and find the push button, and I go off and find the lamp, and I go off and find the serial port. And I bind all these to actual references that I have lying in my code. And so what happens now is that I can actually start doing things with them. And if you look at the push button, I make myself a button port, and then having done that, I can actually bind to events that the button port will produce. The same goes for the lamp. What's going to happen is that the lamp is actually going to be, the program in the emulator will lift the light high to make the lamp come on. And so I have to be told, hey, the program's made the light come on. So what I'm doing is I'm basically binding a little piece of C# called lamp port on GPO activity, and that will then run when the program changes the state of the lamp. So that's the direct connection between my program in the micro framework device and whatever my emulator does with that signal. And this is built, I built this code using IntelliSense because it does all the things with tab that you know and love when you're putting buttons on forms. So I can make myself this thing, I can add another delegate, and away it goes and makes the code. And all I want to show you really is just what happens when we get that code. So I'll just drop through to the actual method call. And what that's going to do is fire a delegate off in the form, which is going to actually show me the fact that the lamp has come on. And so what has to happen now is that the lamp pin has changed state. We must do something to reflect that. And if I dive into the code which actually shows you that, then again, there's nothing particularly complicated going on. I've been given a state. If the state is true, we go yellow. If it's false, we go gray. Now, this is a very simple emulator. If you wanted to have a situation where if the processor lifts this pin, your simulation wants to do some other things to simulate a particular usage scenario, now you can see it's very easy to do that. There's a process that reverses this that binds behind the checkbox. So if I flip the checkbox, I then call a method on the pin to say, hey, your input pin has just changed. And then the program running in my emulator will then pick that up and run with it. So it goes in both directions. It's all in managed code, and it's very easy to write. And just to show you the thing that will get a round of applause, they'll clap this one, trust me, absolutely. They seem like a nice bunch. Then what we'll do is I'll show you the final thing. Now this is to do with we've got this bunch of guys that work in our security warehouse. We don't trust them, which again is kind of, we should probably have a word with PR about that in terms of who, HR, in terms of who they've hired. But moving on, I've got a machine with, again, basically a serial port, an LCD panel, and nothing much on this one. I've got 3 projects in my workspace. This is worth mentioning. It's a little bit hard to see, for which I apologize. I've got the actual project that does the job, which is my flashlight. I've got my emulator, because it's just another solution, so I can put it where I like. I've popped the actual project in here. And I've got my GPS decoder, which is a big chunk of C# that I wrote to decode NEMA streams. And the point that I want to make about that particular piece of code is that it will work on anything. It'll go on microframework, Pocket PC, or the full PC, because it's the same lump of code. In fact, you could take the same assembly and make it part of your project. It's that clean. And so if you're thinking in terms of taking an existing application or building one you want to factor across a whole bunch of platforms, you can do that. You can take the same piece of code and run it on all the platforms. It's absolutely, I think it's just wonderful that you can do that. But as far as we're concerned, all I want to show you with this really is the thing running, because that will actually give you an idea of where we're going with this. Now what I have here is an LCD panel emulation, which is just showing waiting. Now the scenario is that we've got these guys going around the place collecting information, and we want to track them. That's fine. How do we test the code? Well, I've got 3 ways I can feed information to my GPS decoder. I can type in text and press the send button. We've seen that with the actual form. But what I can also do, and this is kind of cute, is I can open up a file. This file, I got this by driving from Howden to York in the UK with a laptop sitting beside me and a GPS puck just bringing in the signal. So it's basically a text file containing a NEMA stream. And if I open it, then what you can see now is we're bringing the stream in. You can see it coming down there. My program in the micro framework is decoding it and putting the coordinates up. And so it thinks it's getting information from a GPS puck, but it isn't. It's coming in down my file. So I can simulate these guys walking around the warehouse. I think that's worth a round of applause. You obviously don't. Never mind, we'll move on. Thank you so much. But the serious thing here, though, is that I've not had to leave the room to test that behavior. And the other thing which I can do, but I can't at the moment because A, we're indoors, and B, I haven't got the puck with me. If you look at the button down here, I can also connect through to a serial port on the PC. And what I've also had running is a GPS puck actually plugged in, sending live streams into my micro framework code. So now I'm chasing position, I'm testing position-aware code, feeding it real coordinates, and a device that I could go off and have built up on silicon for me without having to make anything at all. And I think that's actually kind of cute because it makes it a lot easier for me to actually test this thing. I can build scenarios. I can have a thing where if they go in a certain area, warnings go off, and I can test that. I can salt it with all kinds of things. I could do mapping. I can do all kinds of nice things, and I can test the behavior really low level without having to do any extra work. So that, I think, is kind of cute. And that's sort of bringing me to the end of my demo. And so what I'll do now is I'll get you back onto track again, and things will continue. So I have to do that, followed by that. But I can't really emphasize strongly enough the power that you get with this system. It really, really is nice. I mean, there are challenges because I love the American way of life. We don't have problems, we have challenges. I think it's absolutely great. It's a great way to look at life. There are things you have to deal with. There's power requirements, there's debugging, there's performance tuning and what have you, but you deal with those, and there's a whole bunch of nice ways to do it. I'm going to hand back to Dave now to take us further.
Yeah, because my demos are always...
Because Dave's demo uses hardware. One of the things that he doesn't trust me, this is the thing, because I'm an academic.
He's an academic. Everything is done in the emulator. I mean, have you noticed that? Nothing on real hardware?
It's because in the UK, universities are very poor. We can't afford the real stuff.
Poor. Anyway, so you've seen this. What we can do is we can actually adjust the temperature up and down on here. We've got the ambient temperature on this side. Hey, those of you who were in the previous session would have seen one of these boards. This is a Crossbow iMote 2 board. This actually, you can possibly see on the side, is actually a board with a daughter board strapped to the top of it. It is running full .NET Micro framework. The daughter board, in its own right, will give us motion control, motion sensing. It will also give us temperature sensing. So what I thought here is, hey, let's have a look and see if we can actually hook into some of that temperature sensing. So if I fire up a piece of code here, I just want to show you this, and it is going to be really quick. All of the code that I need to be able to hook into the temperature sensor on that board is there on that one screen. What I've done is I've pulled in the library from Crossbow. I've instantiated myself a sensor. If you look, I'm pulling a packet off of there. And then what I'm going to do is I'm going to squirt that packet, just one of them, down the serial port. And what I'm going to do is I'm just going to run around that loop once a second, grabbing the temperature and squirting it out that serial port. Now, there's one flaw in this demo, which I would have really loved to have been able to solve. You've probably noticed that if I do that, I don't have an RS-232 port. So actually, what I've done here is I've got a USB port sat on the system. And what I'm going to do is actually pipe the input in through the USB onto the PC and then poke it back out through the RS-232 port onto the device. So, you know, I'm using Micro Framework, I'm using .NET Framework, I'm using everything that I've got here. So let's just take it back to the PC and let me just show you what I've got here. So here we go, we've got a console application. This is my proxy. This is all my data. So this has been running throughout the entire session. So you can see I'm running through the buffer at the moment. So if we switch back over to the device, and luckily lights are warm, let's put this under here and see what happens.
It's getting warmer.
It's getting warmer. You can see.
Anybody here with hot breath? We're all computer. Anyone here with laptop fan breath? Come down here and breathe on it, and you might win a T-shirt.
If you can get it over 30, you win a T-shirt.
If it goes down when you breathe on it,
you're dead.
then we might get very suspicious. But I mean, this is a trivial example, but it gives you an idea of how easy it is to connect the interfaces and how easy it is to make use of that information once you've got it.
So we've got two micro frameworks running here. We're proxying it through a PC in this case, but at least gives you a view of how flexible this is. But actually, we could have connected those two devices together through RS-232. One of them would have been squirting out the packets, the other one would have been taking that information back in, and we'd be off. It is so easy to do this sort of stuff. I'll leave you to
Thank you.
wind up.
Okay, question. How many instructions MSIL are not implemented in the 4? Who said 4 then? There's a hand at the back went up. I think you've earned a T-shirt. Who else said 4? Everybody else said 4. Who has said 4? Okay, you said 4. And right at the back, a price for being right at the back and not leaving. There you go. Well done. Thank you. In terms of what we're doing, the .NET Micro Framework, it does two things. It makes it very easy to take your skills and use them on the micro platform. It also makes it very easy for you to make a solution which is very well tested, designed in a very sensible way, which means, as we've been showing, you don't need hardware. You can actually get a very, very long way down. I mean, the business model we were talking about on Monday was that you use one of these boards that you've seen to get your program working. You then go and see your venture capitalist, show him the hardware doing the stuff. He then gives you $250,000. You go off to Taiwan and get someone tooled up to build the custom PCB that you need, and away you go. If you want to, you could actually just start with emulation, depending on how credible you want to be. And you can really go very easily from ideas to solution. But it's better than just a nice place to write code, because you also get all these wonderful features for emulation. So you can build a whole ecosystem around your solution, which you can then hit against with the code. So by the time you ship it, you will have taken your security guard around the world. You will have made him walk around the plant several times. You will have code that'll do all the fiddly bits that will be impossible to do in real life. You will have given your decoder invalid data streams, because you'll have built those and you'll feed them through, and you'll have automated tests that look at what comes back from the device and make sure it always behaves itself. And when you go into production and you've got real hardware, plug the real hardware in and give it the same treatment from your emulation back end. In terms of, if you factor it right, you can do that kind of stuff. The thing about this that I really like is that people will go, I've got an idea for a product, but I can't do it because I can't afford to have someone write the code for me, and I just haven't got the time to do it myself because I have to learn a whole bunch of new skills. As far as we're concerned, that's no longer an issue, because what you can do is you can do it all in the environment that you know and love the best, which is, of course, C# and Visual Studio. And so it's tremendous from the point of view of just empowering you to make stuff, but it also takes it even further than that, and you've got a wonderful place to actually test your idea. Great ideas are good, great implementations are good, but a place in which you can do the proper testing is also wonderful as well. So we're looking at an extremely rich scene to mine in terms of actually producing nice applications. It's very, very pleasing in that respect. Dave's just put up a picture of the prize. So if I do that, I'm going to get it, aren't I? Do that. If you want to get yourself one of those, we're giving it away for the best question, and we're just moving into questions at this point as well. So I think that's just about the end of what we've got to say, because the next one is the Q&A. And so if you want to actually move to the microphones and hit us with some questions, that will be fine. Best question gets the board, and so please don't all run at once. Okay. One thing I will say before you all rush off, can you please fill in your QAs? We want your feedback. We want to know what we've done well and what we've done badly. If you want to give me a hard time for the jokes, as a chap walks into a bar and he hears this voice going, "By gum, you're handsome. Gosh, you look clever. I wish I was more like you." And you look around, there's nobody there. So he says to the barman, "There's people saying nice things about me and I can't see where they are. What's the story here?" And the barman goes, "Oh, that's just the complimentary peanuts." Okay, fair enough. I like that joke. That works for me. But anyway, any questions? I see we have some at that end. So, okay, first question, please.
Can you debug the emulator?
Yes. You can basically bind to the emulator process and you can put breakpoints in there. I have done that. It's a little bit tiddly-twiddly, but it can be done. That's a nice question, yeah. But the answer to that question is yes, you can. If you write your own emulation, you can then debug the behaviors inside that as well, yeah.
Okay, thanks.
Next microphone question.
I saw little bits of in the slide we show which parts are in the micro framework. Reflections up there. Is that full reflection? Can I do stuff like emit and use assembly.load?
No.
Which bits are in there?
It's a lovely thought. Basically, I think that the reflection that is there is the stuff that is there that's going to make serialization work. I can't give you a more accurate answer than that, so a more detailed answer than that, but it's basically the stuff that's required to make reflection work. Anyone care to comment from the floor? No, that's a good question though. But does that help answer the question?
Ish.
Okay. Come and see me afterwards. I'll find you some expertise.
Okay. Can you mention some of the more interesting sensors and extensions for the board you can easily plug in? I know there's the temperature and humidity and maybe cameras and GPS. What about the telephony for sending text messages? Do you know anything about that?
Basically what you get, unless Dave knows better, but basically what you get is the ability to interface down standard serial interfaces to devices. So when we're using a temperature sensor, we use I2C or one of the similar bus technologies to do that. So if you can find a device that gives that behavior that you can interface to in that way, then you can drive it that way.
Okay.
So generally, the board as it comes is a method of interfacing to other things. You get things like motion sensing, you get things like temperature. There's 802.15 Wi-Fi on that. So it's everything that you need to be able to connect it. But then because you've got all of those connected, you can hook it onto other things.
Okay. Thank you.
Okay, next question.
I have two questions. The first is, what's the current status of the project? How stable is the runtime? And what is it moving forward? What's the next version and what's coming?
Okay, you see this on my wrist? This is a Spot watch, which runs on the same technology as MicroFramework. And it goes. I haven't seen any errors in here, so it's solid.
So any Windows Sideshow implementations, they're all based on the .NET framework as well. I mean, what is there is fully usable now. This is a delivered project, and actually moving forward, what you're going to see is things like full TCP stack on there, the ability to do device profiles for web services. So actually, these devices can actually start interacting with other things out there, other connected devices.
Okay. And the second question is that we as software developers, we are not used to build our own hardware. What is the process for getting the hardware devices we need, and how do we package them into things that we could ship?
So you can go about it in a number of different ways, but the way I'd recommend is that things like the embedded fusion board that we've got here, these are prototyping boards. This is actually, let me just, we showed this at the previous session, that this is a prototyping board. Actually, if we flip this over, what you can see on the back, lighting isn't amazingly good, is actually the micro-framework board is this piece here. And actually everything else here is the carrier for the connectors. So what you can do is you can build yourself a solution on something like this, a prototyping board, and then what you can do is, in this case, you can go and speak to Embedded Fusion, and what they will do is they will sell you that piece individually at a much lower price, and then you can have that built into your own applications. So your own solutions would actually include that or a customized version of that.
Will they also help you with the package and the plastic and stuff for?
I'm sure they will. If you contacted them, then I'm sure if they would not help you in their own right, I'm sure they would then have partners in their own right who could do that work for them.
Okay, thanks.
Next question, sorry.
Yeah, your approach looks similar to the TinyOS. Have you analyzed TinyOS and the NESI language? Are there any similarities?
I'm not familiar.
Targeting modes?
I'm afraid I can't comment on that. I don't have any knowledge of that particular one.
But you are targeting crossbar modes, so maybe you have looked at the TinyOS approach.
So in terms of the crossbow solution, that's an iMote board, but it has a micro-framework platform on it. I'm not familiar with the other platforms.
Okay.
Final question.
Hi, this technology is great for network sensors, but is a lack of something, the web services. There are some way to put that in this version or future revisions for that?
So just to clarify that question, are you saying that is it possible to deploy code onto the device such that you retain your intellectual property on there and other people can't deploy?
No, not that.
I think, was it web services you were asking about?
Yes, web services.
Because I basically say, Dave will now tell you about web services on the micro-frame. That's a really nice question, actually.
So in terms of device profiles for web services, then the whole point of the micro-framework is these are connected devices. And actually there are bespoke implementations out there now. So in terms of Digi have a solution called the DigiConnect ME board, which is a network-hosted, network-powered solution where the whole thing sits effectively within a network hub. very, very small device. Now, at the moment, they implement their own version of the TCP stack in there. Moving forward, the micro framework is actually going to implement IP stack in its own right and device profile for web services. So that's the sort of things that you're going to be looking for in the next versions.
Okay, thanks.
That was actually my favorite question. And so for that, you've won yourself a micro framework board. Give the man a round of applause.
I've got a...
Oh, another question. Oh, sorry. Okay.
Oh, there's more.
Oh, no.
Oh, no.
Looking in the shadows. Okay.
It's all right,
away.
I'm not just in it for the board. Is the framework tied to any particular CPU architecture? If not, have you, does it target any of the runtime acceleration features in some architectures, such as Giselle on the ARM or similar?
I know it isn't tied to any particular platform. I can't talk about what it may or may not target on the platform, I'm afraid.
Actually, there's a porting kit available for OEMs who want to deploy the micro framework onto their platform. And what that enables you to do is be able to deploy the .NET micro framework onto either an existing operating system or directly down onto the silicon. Now, actually, in that integration, when you do that, there's nothing to stop you capitalizing on any inherent functionality that there may be there, so that you can utilize any optimizations that are on the board. One example, not directly relating to silicon, but if you have hosted it on a real-time operating system, then you could actually inherit some of the determinism out of the real-time operating system into the micro framework. And the same is true if you were going to try to pull on some optimizations that were actually on the silicon.
Thank you.
Can I program against micro framework using other languages, .NET languages than C#?
Not at the moment, no. It's C# or bust, which...
And are you going to enable us to program Visual Basic and other dynamical stuff like Iron Ruby, Iron Python, and so on? It's all .NET languages.
They are all .NET languages. At the moment, we only support C#. Now, you know that .NET compiles down into IDL, so whichever language that you use, in theory, could be utilized on the micro framework, but at the moment, we only support C#.
Thanks.
I have a question regarding operating system. You said there's no operating system on this one, but we can have multi-threading. How does that work? And how many threads can we have running at the same time?
I don't know what the upper limit is. Basically, it arbitrates between the threads inside the process of emulating the actual instructions. So it's not done on the basis of an OS. I mean, the same mechanisms are used, but just not that it's an OS doing it, it's a runtime system doing it, if that answers the question. So it basically is part of the execution engine, which does the multitasking. It doesn't base itself on what the OS gives it. Is that a reasonable?
Yes.
Yeah.
Yes.
Thank you.
We're actually out of time.
Okay. Now we have to give the man his prize. And thank you very much for coming and staying this long. And give the prize.